Well, hey everybody, welcome back to a new part on this series I'm doing on converting this Volkswagen Bus to all electric. Well, in our last video, we got our MCU to recognize our charger and we were able to start charging. I wanted to create a video this time to follow up on that in between our video on the state of charge gauge or our instrumentation. What we're going to talk about in this video is some more warnings around parallel packs. Then I'm going to show you how I configured the MCU to recognize the fact that we have multiple packs, not just one pack, after we connected all these measuring and balancing boards. Then I'm going to show you how I was able to do the top balance of the charge and some more information around that. And then finally, I'm going to show you how I fixed an issue where my level 2 charger wasn't being recognized as a level 2 charger, and therefore we weren't getting the charge current or wattage out of it that I expected. So stay tuned. Okay, so in the first part of this video, I want to talk more about parallel packs. In that video I talked about on battery pack design, I did discuss parallel packs and the limitations or the warnings about not doing high voltage parallel packs. One of the big issues I talked about with regard to high voltage parallel packs was the eddy currents that go between them. Well, with this video, I also wanted to share with you some other potential issues you could have, because that way you have all the information on why you would not want to do parallel packs. Now, one of those is the fact that this pack right here is all in one place. It's very tightly coupled together. There's only about 7 inches of space between the main parallel connections on these parallel packs. Now, that's only because I have a truck suspension in this Volkswagen Bus in this rear here that can handle a lot of weight. So this is not a problem for it. But in many other cars, especially smaller cars that people convert, you have to separate the battery packs between the front and back to get distribution of the weight. Otherwise, you might have to make major suspension changes. In my previous EV, which was a Triumph Spitfire, that's a good example one. I had to split my battery pack up into about 40% in the back and about 60% of the batteries in the front. And even then, those 40% batteries that took up the space of where the fuel tank was, I still had to make slight modifications to extra 70 pounds it added to the suspension. So smaller cars, the suspension needs are much greater than these larger cars where it can take hundreds of pounds and no big deal. But that was a single series pack. In other words, the disconnect between the packs was a single wire between a series connection in the rear and the back. When a series pack is discharged, the current has to flow through the entire pack as one. So even if you have different ampacities between bus bars and different series connections, it still, doesn't really affect each module individually that much. So that's totally a fine and valid situation. But imagine you had to split these packs up in a small car in these high voltage parallel packs. Now you've got a pack in the rear of the car, say, that has 2 long cables, the positive and negative, between the front of the car. The motor controller, if it's in the front of the car, might favor a little bit more in terms of current that front battery pack because of the ampacity of the wire between the parallel connections. It may be a few milliamps, but over time that could become a problem. And then there's also just individual cells. If you have individual cells that are having trouble, parallel packs can potentially exacerbate those type of situations. Now, I linked in my video description a really comprehensive guide to parallel packs written by a company called Orion, who makes a very industry standard BMS for EV conversions and for the EV industry. Their recommendations are pretty extensive. I read that a little bit, but it's really geared toward electrical engineers. And it was talking about things like, multiple pack contactors, multiple dedicated BMSs for each individual pack, power diodes and things for limiting eddy currents, and those BMSs being able to talk intelligently together to work those contactors. And they also discuss many other limitations of parallel packs. It'll probably scare you, but maybe for good. Now, when I was talking to Thunderstruck support about a myriad of questions that I had, and their support is excellent. I really like those guys, which is why I recommend their products. One of them watched my video that I did on the MCU, where, that first video I did where I showed the wiring of it and how to connect to it. And he gave me very positive notes. He said that, the teaching was very methodical and great, and I really appreciate his feedback. The one note he gave me was not even based on the MCU instruction, but on the fact that I had these independent parallel contactors on my battery packs. He recommended against it, and I wanted to let you guys know that, and I'm going to show you the change that I made. I got that idea from Orion, but because I didn't implement all the other ideas from Orion, he said that it's better just to hardwire these parallel packs together. Probably because of long term, as they degrade, it's probably better just to leave them hardwired together, so that if, I let them sit for a while and maybe they imbalance themselves when they start getting older, and I slam them together with these contactors, that could be bad. So that will probably mitigate that. Now, yes, the recommendation from Orion was to put separate contactors on, but I didn't implement that fully, and that's the problem, right? I would have to have separate independent BMSs that know how to deal with parallel packs like Orion offers, and they have to talk to each other and manage those contactors, not just have the contactors close like I had it. So I went ahead and did the recommendation from Thunderstruck Support Engineer, and let me show you what I did. What the big change that I made here was just to hardwire the packs, was simply to remove the contactors from my second and third pack here. Now, as you can see, no more contactor, and I'm bridging right on the fuse. They still recommend having separate high voltage fuses for each pack, but not contactors just wired together. Now, on that first battery pack, notice I left the contactor in there, but what I did was I moved the cable that connects pack 2 up to the fuse side of that contactor instead. The part of the contactor that goes into my distribution box still is on the other contactor terminal. What that means is packs 1, 2, and 3 are hardwired together, but they're still a contactor between all 3 of the packs and my high voltage junction box that's in here. So I still have that extra contactor for safety, so that if I pulled all the contactors out, I would only have that one main contactor in the back for my controller, but now I still have a pack disconnect contactor and that controller contactor. In my high voltage junction box, the only change I really had to make here was to remove that little fuse panel that were for my individual pack disconnects, and simply, I still have that relay and all the other programming that I showed you in the MCU, but it simply just drives this one contactor that, again, just has to close on charging or driving, but it's for all 3 packs, not just for the one. I should also note that when I made these hardwired parallel connections here, that I did wear heavy-duty gloves, because even though there was no sparks and I had these packs top balanced, and we'll talk about that later, and initially I was just wearing nitrile gloves plus an extra layer of these removable nitrile gloves, and that gave me the dexterity to work the nuts. And again, knowing that there wasn't a whole lot of eddy current going through these connections, but I wanted to make sure I protected myself. So again, I just want to say that parallel packs is not the ideal situation. I'm making this calculation for this particular scenario just because, like I said, I can mitigate some of that, but these being new modules, these being all close together, not separated, and these being high discharge and high charge current type of modules that can handle this type of parallel pack possible abuse. This is also a situation of money, right? Because this pack right here cost me, after I figured in taxes and the shipping charges and things like that, and take out the 2 modules that I didn't use, the 8 that I originally bought, this pack cost me $1,700. Now, to get a 30 kilowatt pack, in terms of pricing, the ideal situation would be like maybe Tesla modules, Hyundai Ioniq modules that are also 5 kilowatts per module, but they're low voltage modules, they're 23 volts, so you could do a pack of 6 or 7 of those and have a equivalent 30 kilowatt or plus pack, but not have to parallelize your modules. The problem though, again, the cost. Even if I found 6 or 7 used Model S modules for a low cost, like meaning they only had maybe a 50 or 60% capacity left on them and they're in a high mileage car, that would still cost double what these cost. So it's really about what I'm hoping to get in terms of value over the long run. Okay, so that's everything about parallel packs that I wanted to warn you about. But now what I'm going to do is I'm going to show you what I needed to do to tell the MCU that we had 3 parallel packs. Last time when we connected all the measuring and balancing boards, what ended up happening is the MCU knew that I had 156 cells across 12 measuring and balancing board, but what the MCU didn't know was how they're configured, right? It just assumed I had like a 530 volt pack, that all 156 cells were in series, when that's not the situation. It's 370 volt packs. So let's talk about what I had to do on the MCU to have it recognize these as 3 packs instead of 1. Okay, so what I had to do in the MCU was first I went to page 32 of the MCU manual where it starts talking about parallel packs and mapping. This will introduce us to a new prompt context called BMS. And there's a new command called CMap within that BMS thing, which talks about how we map our physical measuring and balancing boards that are in the order that they are to the logical order that we want them in. And not only that, but also what packs they should be in. Because again, when we wired up our measuring and balancing boards, this is how we have it looking here, out of the MCU, I decided to go to on the left-hand side, and that's the first measuring and balancing board, which is over here. Then we jump over to the second and then third, and you can see that the numbers that I have here are the ordering in which we wired our measuring and balancing boards physically. But how we wired them physically often has no relation to how we think of them conceptually. Because conceptually, the way I think of this is we have 3 packs. The first pack being the measuring balancing board 12, and then 7, 6, and then 1, going from left to right. Then the second pack is 11, 8, 5, and 2. So to give you an idea, when I went into the MCU and I looked at my packs, I went to the BMS context first by typing BMS, enter, and then I put SH. And notice now it says pack 1, voltage 173, pack 2, same thing, pack 3. And the total is 156 cells. When I initially did this, before I did all that mapping, it said there was only 1 pack and it was 530 some volts and 156 cells. Because again, the measuring balancing boards doesn't tell the MCU how the actual modules are arranged in a pack. It just assumed that there's 12 measuring balancing boards, 156 cells, they're all in series to make a 530 some volt pack, but that's not reality. So what I had to do was issue a bunch of these CMap commands. And let me explain exactly how I did that. So going back here, they give an example, set CMap, and then there's 3 parameters. The first parameter, and I'm not sure what A3 and A4 mean, but for the measuring balancing board, it's simply the number of the measuring balancing board, 1 through 12. So the first parameter is the number of the measuring balancing board. The second parameter is the pack you want it to belong to. And the third parameter is the cell group you want that to map to. So in my case, I want pack 1 to consist of measuring and balancing board 12 as the first cell group, then 7 as the second cell group, then 6, and then 1. So the way I did that was I did, and I won't do this now, but I simply said set CMap 12 space 1 space 1. What that means again is measuring balancing board 12 should be part of pack 1 and the first cell group of 1. So 12, 1, 1. Then when I went to did the second one, I went set CMap 7, 1, 2. And again, that means the 7th one here should be logically part of pack 1, cell group 2. And then I did it again for 6, 1, 3, and then 1, 1, 4. And that's how I did that. I issued 12 different commands there to reorganize all of the logical measuring and balancing boards into these 3 packs so that it understood that. Now, this did not affect my charging. My charging profile, which again, for review, is under the EVCC prompt, is still 182 volts or 3.5 volts per cell. So it's not like by the MCU thinking I had a 530 some volt pack, it, you know, charged differently or whatever. But what it would do is show an incorrect display on our state of charge gauge. Notice also though, and I'm not going to extensively talk about all this BMS stuff, but if you go to page 99 where we start talking about all of the different commands under that BMS context, that notice that we have, you know, show CMAP, show cells, all that stuff, but we also have stuff like set low pack voltage, set high pack voltage. So even though it assumed I had a 530 some volt pack and only one pack, I don't think it set all these low pack, high pack conditions, but I will probably have to go through and set a lot of these parameters so that alerts and other things like that will be more accurate for my particular battery configuration. Okay, well now that we're done talking about parallel packs, the issues and the configuration, let's talk now about charging. In my last video, basically all I got done at the end of the video was I got it to recognize my charger and I got to start the charging process. Now what I'm going to show you is a few changes I made in the MCU to give a little more definition around the charging and around how I did top balancing, and show you an issue that I ran into and how we're potentially going to fix it. So the first thing I did was, while it was charging, I had no idea what the state of charge is in my pack. Like I mentioned before, the state of charge video will be probably my next video here, so I don't have any instrumentation to show me anything. What I did was I issued a command in the sysprompt, which was basically set out 1 to fuel G, or fuel gauge. Now I mentioned in my previous videos about how to custom program those outputs, and the way I showed you is how to use those outputs as Boolean type switches, where it either turns it off, meaning it's not connected to ground, or turns it on, meaning it's connected to ground, and you can use that in conjunction with a relay to do switching of external devices. Fuel G and temp G are specialized ones that aren't just Boolean resistance values. What they are resistance values that simulate, for a fuel gauge, the sender resistance value of an analog fuel sender. Or on the temperature gauge, a thermistor resistance value that simulates an analog temperature gauge. By setting output 1, since I'm not using it right now, I can at least see internally when I do a SH command on sysprompt what the current state of charge is on the pack. The second thing I did was I enabled the top balancing option. If I show you the config, you could see that now top balancing is added to my charge profile. All I did to do this was type in enable top balance and then hit enter, and then it added to my profile. Simple as that. Now one thing I want to note is, I mentioned in the last video when I was talking about chargers, is my previous EV charger that had lithium iron phosphate batteries had a finishing charge profile set up to it. It was 3.5 volts per cell up until a finishing charge of 3.65. Now I was given no indication by Thunderstruck or no recommendation to do any type of finishing charge. And I'm not sure if that's due to the fact that it's the A123 batteries don't require it, or if it's because the MCU top balancing doesn't need it, or if it's just maybe I'm stuck back 12, 13 years ago and it's no longer industry standard to do any type of finishing charge on any lithium chemistry. I'm not quite sure the answer to that is, but I'm still just doing 3.5 volts per cell or 182 volts total, and I just enabled the top balancing option and the MCU took it from there. Now don't ask me to explain how that top balancing algorithm works. I have no idea. But all I know is that kind of turned on and off the charger at different intervals, and eventually it kind of top balanced the pack. Once I did this and I did a show cells, a lot of batteries showed as pluses and all sorts of things. There was all sorts of high voltage conditions on lots of cells. But then after, you know, the temperature dropped and I drove it around in my driveway and I backed it into my bay here, my state of charge now shows 99%. And you can see when I do show cells, there's only one really cell in the second pack that's a little bit low, and everything else is fairly well balanced. Now one issue came up while I was charging, and let me describe that now. When I initially plugged in my charger, I had my little 110 volt charger, and this is actually one came with my Volt. It is only a 1400 watt charger at 110 volts. Then I have this other one, which I've always called my level 2 charger, but now I'm not quite sure what to call it. This is 220 volts, and it's at 16 amps. Now I always kind of considered like level 1 charging 110 volts, level 2 charging is 220 volts, and level 3 charging, I guess, is maybe 3-phase AC. But I don't know if it's that simple. Let me explain why. I mentioned before that the proximity pin on these chargers kind of gives an indication of the amperage capability of the charger. When I looked at our proximity pin, while I'm charged in, if I do a show, the proximity pin on this charger shows 150R as the proximity value, and this one has 145R. So there must be some more detail around the difference between a 12 amp charger and a 16 amp charger. But what there is no designation of what is 110 volts or 220 volts. In my opinion, they should use the proximity pin to determine total wattage that the charger is capable of, because it doesn't really matter the voltage. What matters is how much amperage and voltage is capable, or in other words, wattage, that's capable for the charger to use, because the charger is going to have to transform the voltage anyway. So now the problem. What I noticed was on this 3,500 watt capable charger, it was only charging at 1,500 watts when I looked at my charge trace. Now that's 1,500 watts on the output, or just around 8.5 amps. But this is capable of 16 amps. I would have thought I could get the full 3.3 kilowatt charging output out of it, but it was only doing 1,500 watts. Now what Thunderstruck told me is their algorithm is using a 16 amp heuristic to kind of determine, because we're not given voltage, 16 amps or under is pretty much considered level 1 for them. So this one being a 16 amp charger, and typically level 2 chargers start at 20 amps, and the most common ones out in the wild are 32 amp chargers, which are capable of 7,000 watts. What I'm seeing a lot nowadays that's pretty common is people, instead of buying a large, like for example a 6.6 kilowatt Elcon charger, instead to buy 2 smaller 3 kilowatt chargers. And the MCU has an example of a dual charge profile on their documentation. Now this one uses their 2,500 watt charger, and there's 2 of them. And what they show here is that you can have one charger set up with no line voltage or current requirements, and the second one with a line voltage and current requirement of 220 volts at 25 amps. What I imagine this does is when you're at home and you're charging with some smaller charger like this, you're going to be limited to 1,500 watts, and only one of the chargers is going to be enabled, because why enable the other one? It's not really needing to do anything. If you go to work and you have a commercial level 2 charger that's 32 amps, then when you plug into that, this charge profile will turn both chargers on. You get the full 5 kilowatt charging capability. What I'm stuck with is I have this 3,500 watt capable charger here. MCU just thinks it's a level 1 charger and caps it off. I asked Thunderstruck about this, and what they recommend is maybe I try to add to my charger profile a line voltage of 220 volts. Maybe the hope is, the hack here is that by saying that it's a 220 volt charger, that any charger plugged into it will be considered kind of a 220 volt charger, and they'll pull whatever maximum amperage they can out of it. That's my hope. So what'll happen? Let's see. What I'm going to do is I'm going to issue a command, set line V 220 on the EVCC prompt here. My hope is that, like I said, it will allow me to pull full amperage out of my 220 volt charger, and we'll see what happens when I plug in my 110. My hope there is it'll still just pull 1,500 watts out of it, because if it's the only charge profile, I think it'll still charge, but I just don't know what it'll do. So let's kind of see that. Okay, now let's try to plug in our 220 volt charger and see what happens. So we're going to let our charge ramp up, and we're going to see if we can get higher than what it did before. And oh, it looks like it's working. We already are achieving much higher than 1,500 watts here. Let's see where we top off at. Nice. Looks like we're around 3,000 watts. That's what I expected. So great, that little hack worked. Now let's see what happens when we plug in our 110 volt. Okay, hold on. So now this 110 volt charger was a 1,400 watt charger on the input. 12 amps total, but it looks like we can even get more out of this one. This one is topped off at about 1600 watts on the output side. So great, that means that we can get more than 1500 watts out of both of our level 1 and level 2 chargers, and they still work on this single little 3.3 kilowatt charger profile. Well, in conclusion, we got our charging issue fixed. Again, this is the situation where you have under a 20 amp charger, which is not recognized as a level 2 charger, but it still supplies enough output power for this 3 kilowatt charger. You can set your line voltage on your single profile to 220 and it'll pull the maximum amount of amperage out of that charger. Now, I also, when I plugged in the 110, noticed that it was pulling about 1600 watts when this is really rated at 1440 watts. So a level 1 charger that may not be able to handle 15 to 1600 watts may be driven a little hard, even though it does work. But the reality is I probably won't use this charger on this 30 kilowatt pack. It's really too small anyway, and it will take forever to charge it. So I'll be sticking with my level 2 charger and probably getting another larger one in the future. So our next video will be on the state of charge gauge, and that's why we did some configuration in here to get set up for that. Notably, we're putting those CMAP settings in so we have the pack situated correctly, and we set our out one to the fuel gauge setting to drive an analog gauge. What we're going to do in the next video is show side by side how to do a CAN bus enabled gauge and a classic analog style gauge so you know which option works best for you. If you haven't subscribed to the channel, go ahead and do that now so you're notified that the next video comes out. And until that next one, I'll talk to you later.